Okay, so hello and welcome everyone to the last week or week 13 of interactive live sessions for the course on fundamentals of convective heat transfer. This course is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and a TA for this course. So, like every other week, we will solve some problems together, and this will be a revision class. So, we will cover topics related to all the 12 weeks of lectures that we saw. So, let's get into it. Let's get into revising everything through a few problems. So, this is problem number one, which pertains to the very simple first thing we learned, Newton's law of cooling. It's asking us that Newton's law of cooling states that the rate of heat transfer between a surface and a surrounding fluid is proportional to what? So there are now four options given here. One is the temperature difference between the surface and the fluid. Option B is the surface area of contact. Option C is convective heat transfer coefficient. And option D is all of the above. That is, all A, B, and C are proportional to or Newton's law of cooling is proportional to all of them. That's what it means. So read the question carefully and pick out your correct option. So let's quickly take a look at the solution. It is indeed all of the above. So let's say we determine or we denote the temperature difference between the solid surface and the fluid by delta T, which is also equal to, let's say, T wall minus T infinity, where T wall is the surface of is the temperature of the solid, and T infinity is the temperature of the fluid. Then surface area of contact, it is denoted by A, and the convective heat transfer coefficient, which is denoted by H. This was the all important parameter which we were trying to study. So now Newton's law of cooling states that this rate of heat transfer is actually proportional to all of them, H, A, as well as delta T. So you can combine all of them and write that rate of heat transfer is actually equal to H, A, and delta T. So each of them increases, rate of heat transfer increases. Any of them decreases, the rate of heat transfer will decrease, and proportionately. So that's Newton's law of cooling for us. Now let's move on. We'll move on to question number 2. It's a match the following type of question. So we have dimensionless numbers which we came across in the left hand column and their formula in the right hand column. And all the symbols mean the general things which we typically use. So, for example, beta is the coefficient of expansion, g is rate of acceleration due to gravity, L is the characteristic length scale, delta T is the characteristic temperature difference, H is the convective heat transfer coefficient, K is the conductive heat transfer coefficient, and so on. Nu and alpha are the momentum and thermal diffusivities, respectively. So I guess I've listed all of them by now. So different combinations of these dimensional quantities will give us some dimensionless numbers, which which become important for different cases which we studied. So here is a list of those numbers: Nusselt number, Prandtl number, Grashof number, and Rayleigh number. You have to match them with the correct corresponding formula for each of them. So let's take a look at the solution. Very simple. So Nusselt number is simply the dimensionless convective transfer coefficient, HL by K. Prandtl number is the ratio of the properties of the fluid, so nu over alpha. The momentum diffusivity over the thermal diffusivity. Grashof number was this. It was the ratio of the buoyancy forces versus the inertial forces, or sorry, viscous forces. And Rayleigh number was this. it was a product of Grashof number and Prandtl number. So Rayleigh number you can simply find as the product of Grashof number and Prandtl number. So you see there's a nu square here. If you multiply it with mu over a, one nu cancels out and you get another alpha here in the denominator. The numerator remains the same. Simple stuff. All right, so let's move on. We'll move on to question number 3 now, which is asking us which of the following. So there are 4 different cases of heat transfer given. So which of the following is an example of natural convection? Is it option A, cooling a hot plate with a fan? Is it option B, heating a room with a radiator? Is it option C, cooling a car radiator with air flowing through it? Or is it option D, heating water in a pot on the stove? Let's take a look at the solution. It's option D. So we will go through each of these cases. So cooling a hot plate with a fan, what do you think it is? It should be forced convection since you have a fan, right? Which is forcefully blowing air over it. Then heating a room with a radiator. As the name suggests, the main form of heat transfer is through radiation. Usually infrared rays are used. Then cooling a car radiator with air flowing through it. Once again, there is some radiation involved, and the other dominant mode of heat transfer here would again be forced convection because the car is moving and therefore forcing uh, air to move over the tubes of the air car radiator, thus cooling it. So here again, it's an example of a forced convection. Only option D is an example of natural convection because from the stove to the pot, it goes through conduction through the material of the pot. But then from the pot to water, that heat is transferred, in a natural way. So if I draw this thing, so let's say this is where you're heating it. So this bottom surface will heat up and cause the hot water to rise up after becoming, less dense, and the cooler water from top will now come down, and it will hence set up these natural convection currents, leading to the main mode of heat transfer being natural convection, being through natural convection. All right, so that's why option D should be the correct answer. Right, now let's move on. We'll move on to question number 4. This is a numerical type question. It has given us, an assumption of a boundary layer velocity profile, specifically a cubic profile. So we have 3 terms over here. We have to find the ratio of its displacement thickness to its momentum thickness. Okay, so let's do this. We will do each one by one. So displacement thickness, let's denote it by delta star, and momentum thickness by theta. What we finally have to find is a ratio of this, which is also known as the shape factor. So the ratio of displacement thickness to momentum thickness. Now we need each of them individually. So let's solve for them. I will write over here for the lack of space. So delta star is integration of 0 to delta 1 minus u over u infinity dy. So now we will simply replace this u by u infinity with the form that we have. So it's an integration of 0 to delta 1 minus y by delta whole cube plus 3y by delta squared and plus, sorry, not plus, it will be minus here. It will be minus, yeah, sorry. So it will be 3y by delta. And with respect to dy, we have to integrate this now. So let's integrate each term one by one. So the first term first term 1 becomes y. Then the second term is we have delta cube in the bottom and y cube on top. So that simply becomes y to the power 4, and there's a 4 over here. Then we have 3 delta square in the denominator, and y squared, let me write this 3 over here, and we have y squared. Integrating it would lead to y power 3 by 3. These two 3's will cancel out. Then we have minus 3. I'll write this in the numerator. I'll have 3 delta in the denominator. I'll have y squared and a 2 over here. So now, okay, so I have actually integrated these things. So it will go from 0 to delta, and if I simply plug in delta, I'll get, and I'll take delta common. So let me write it this way. So I'll take delta common. The first one is delta, so what is remaining is 1. Here, this term becomes delta cube, delta to the power 4 by delta cube, so only one delta remains, and the fraction is 1 by 4. So 1 by 4. And as I said here, it becomes 1, and this one is 3 halves. So simply, wait a second. Okay, so I have 1 plus 1, 2 minus this whole thing. So if we take 4 as the common denominator, so we have 4 minus 1 plus 4 minus 6. So 4 plus 4, 8 minus 7. So we have 1 in the, uh, wait a second. Yeah, so what we have is finally is that delta star is equal to delta by 4. Right, this is the first finding. Now a bigger calculation. Now we have to find what theta is. So theta is 0 to delta u by u infinity multiplied by 1 by 1 minus u by infinity dy. Now we will simply plug in the form which we have assumed and then take a product of them. So we have y by delta cubed minus 3 y by delta squared plus 3 y by delta. Then we will take a product with 1 minus y by delta cubed plus 3y by delta squared and minus 3y by delta. Now we will take a product of all these terms. So we have 3 multiplied by 4. So we should get 12 terms over here. Let's write them out carefully. So first we will multiply everything with y by delta cube. All these 4 terms with y by delta cube. Let's see what we get. So first will be y by delta cube, that is minus 1. Then we will get y by delta to the power 6 plus 3 y by delta to the power 5, then minus 3 y by delta powers 4. Okay, so the first 4 are done. Now next 4 we will multiply all those terms with minus 3 into y by delta squared. So the first term becomes minus 3 y by delta squared. Then the second term we will get plus 3 and y by delta powers 5. Right, 3 plus 2, 5. Yeah. Then the next term will become negative. So it will be minus 3 into 3. So 9 and y by delta to the power 2 plus 2, 4. Then the last term will be plus. Again 3 into 3, 9. We have y by delta, power 1 plus 2, so 3. So these four terms are done. Then again we will multiply with 3y by delta. Let's see what we get. So the first term would be 3y by delta, then minus 3y by delta power 4. Then then we will get plus 9y by delta, 2 plus 1, 3. And the last term would be minus 9 y by delta powers 1 plus 1, 2. And this whole thing has to be integrated with dy. Alright, so now okay, so I'll skip one step over here. So I will integrate each term and I'll take delta common. As you can see that, the order of y's and deltas are same in each of these terms. So integrating them once will increase the order of y by 1, and delta would remain the same. So all these terms, after we integrate and take one delta common, they will all be pure numbers. They won't have any dimension. So let's take delta common and then perform the two steps, that is integration and then plugging in delta. So we can simply do it this way. So the first term would be y cube. So that should, after integration, give us 1 by 3. Then the second term should give us 1 by 7. The third term has a 3 up front, and the integration would give us 1 by 6. Then we have 3 up front, and integration would give us 5. Then we have 3 up front, and sorry, so we have 3 originally, and integration would also give us 3. Then we have 3 over here, integration would give us 6. Then we have 9 here, and integration would give us 5. Then another 9, integration gives us 4. Then we have 3, integration gives us 2. Then we already have 3 and y to the power 4, so integration gives us 5. Then we have 9 and integration of 3 gives us 4. And finally the last term gives us 3. Alright, so now we have to simplify this. As you can see, let's see. Okay, we might have to go through a few steps before we can do this. So delta first term is 1 by 3 minus 1 by 7 plus 3 by 6 can be written as half. I have a 3 minus 5. I have a 1. I have another half. I have a 9 by 5. I have a 9 by 4. I have a plus 3 by 2. I have a minus 3 by 5. Okay, these two minus 3 by 5s, let's arrange them. Or what we can do is we can take a common denominator and do this whole thing. So we have 3, 6, 4, 5, and 7. So what do you think would be the common one? 42 into 5. 42 into 5 should give us 210. Is that the minimum? 210, 210 by 2 should give me 105, but that's not divisible by 2. So yeah, so we have to do 210. So I'll continue here for the lack of space. So I have theta, which is equal to delta, and the whole thing that I'm taking, sorry, So I'll take everything common under 210. So the first one, 1 by 3 has to be multiplied by 70. Then I have 1 over 7. So that is 30. Then I have half basically. So half would be 105. Then I have 3 by 5. So 210 by 5 gives us 42. And 42 into 3 will give us 180. 42 into 3. So 120 and 6. So 126. Then this term 1 would give us plus 210. Sorry, minus 210. Then again I have a plus. So it will be 105. Then I have 9 by 5. So that is 9 into 42. That is 42 into 9. So 420 minus 8. And 41 minus 4 gives us 378. This is becoming way too messy. Okay. This term. Then I have 9 by 4. 210 by 4 gives me 210 is not divisible by 4 as well, huh? Okay, I'll just do this whole calculation and come to the final answer. So excuse me for this, I'm going to use some tool in order to do this. So I guess we can do this in Google. Wait. 1 by 3 minus 1 by 7 plus half. Let's see if this works or not. Yeah, it does work. Plus half minus 3 by 5 minus 1 plus half minus 9 by 5 plus 9 by 4 plus 3 by 2 minus 3 by 5 plus 9 by 4 and minus 9 by 3, which is 3. Yeah, so the answer comes out to be this. Let's look at, can be, I don't think this works. Let's try an AI tool for this, huh? So we will copy our search, put this over here, and let's see what it does give a solution, but this does not look okay. Anyway, so let's stick to this point 0.19 basically. So we can write that theta is, sorry. So we can write that theta is equal to 0.19 delta. So the shape factor would be, oh, I've written shape factor. So the shape factor will be 0.25 delta divided by 0.19 delta. So this should also give us some clue to what this number could be. 0.25 by 0.19. Let's assume 0.2. So this will be close to 5 by 4 or 1.25. That's the shape factor which we are looking for. Okay, so let's move along. We move on to question number 5, which is asking us that is telling us that the local shear stress at the wall for flow over a flat plate is given by this equation. If the length of the plate is doubled, or sorry, if the length of the plate is increased to 4 times, then what happens to the total friction force F? Is it option A doubled? Does it remain the same? Is it option C halved? Or is it option D becomes 4 times the original value? So make sure you're understanding the problem that I have a plate like this with some flow coming in, a classical boundary layer problem. So here uh, there is a expression for the local tau, sorry, the local shear stress here, which is given by K by root x. Now due to this there is a total friction force on this plate, right? Now let's say if the length of this was L and I take another flat plate which has a length 4 times the original value. Once again a same uh, inlet flow comes in, a boundary layer forms. What I'm asking is that this also experiences a total friction force F. I'll call this F2. So, and let's call this F1. So what I'm asking is, what is the relationship between F2 and F1? So F2 and F2 by F1, what is it equal to? So the ratio F2 by F1, if it's 2, then it's doubled. So it's 2. Is it 1? Is it half? Or is it 4? That's the question. What do you think it should be? Let's take a look at the solution. It becomes doubled. Let's see how it goes. So we know tau, that is K. I'll write this a bit differently. So it's equal to K x powers minus half. Right? That's what it means. Now let's calculate the total force. The total force is 0 to L, this tau, into some width, which we will assume as 1, into dx, right? Not only, yeah, so the area is W into dx. And you have to multiply the area with the shear stress to find out the shear force. And that is for an elemental, area of length delta x. Then you find it for this whole plate. by integrating from 0 to L. So let's replace tau w by the known form, and this should give us x power half by half. Sorry. So x power half by half, and it goes from 0 to L. So F1 will be equal to 2k into x, sorry, I'll put L here, so L powers half. Now that's F1, and what should F2 be then? And F2 should be 2k, then instead of L, we will replace this with 4L because it became 4 times its original value, power half. So let's take a root of 4 outside, so that will be 2, and we have 2k L power halves inside, which is nothing but F1. So our ratio F2 over F1 becomes equal to 2. Excuse me. So that's why the force should be doubled. I hope that's clear. Let's move on. We move on to question number 6 now, which is asking us which of the following regimes is characterized by the highest heat transfer rates. Is it option A, natural convection? Is it option B, nucleate boiling? Is it option C, transition boiling? Or is it option D, film boiling? So these are, regimes of pool boiling, right? So we saw the plot of how heat transfer rate varies with excess temperature T, delta T. You have to find, this question is asking which of these regimes is associated with the highest rate of heat transfers. Is it option A, natural convection, option B, nucleate boiling, option C, transition boiling, or option D, film boiling? So let's take a quick look at the answer. It's option B, nucleate boiling. So if we go back to our pool boiling curve, where we had delta T in the x-axis and Q, the heat transfer rate, on the y-axis, it started off like this. Then in the onset of nucleate boiling, it went up. Then in transition, post-transition, it dropped down to the Leidenfrost point and again went up. So among all the options given below, this is the point where it reaches the peak, right? And that is associated with nucleate boiling, which is why options B would be the correct answer. Right, so let's move on. Move on to question number 7, where it's telling us that for a turbulent boundary layer, the friction factor is given by such a form, where it's related to the Reynolds number in this way. We have to use Colburn analogy, which relates heat transfer to fluid flow, and find the Nusselt number. Given that Colburn analogy is also given by this, that Stanton number into Prandtl number powers 2/3 is equal to CFX, the friction factor, by 2. And the definition of Stanton number is also given. It's the ratio of Nusselt number with the product of Reynolds and Prandtl. You have to use that and find out what is the Nusselt number NU. So you see the broader picture of this, right? So if we already know what the friction factor is, we can simply use the Colburn analogy to find what Nusselt number is. So let's get to work. So we will start with Colburn analogy, that Prandtl number into, that Stanton number into Prandtl number powers 2/3 is equal to CFX by 2. Then we will replace Stanton number by its definition here. So it should be Nusselt number by Reynolds number by Prandtl number into Prandtl number powers 2/3, and we have CFX by 2. Let's replace CFX by 2 with this formula here. So we will replace this with K into REX minus 1 by 5. Now taking everything other than Nusselt number in the other side, so we have K here, these two Prandtl numbers, if we take care of the indices, it becomes power minus 1/3 on the left hand side, and once we shift it there, it becomes powers 1/3. and Reynolds number is powers minus 1 here. If we shift, it becomes 1, and 1 minus 1 by 5 is simply 4 by 5. So using Colburn analogy, we could find what the Nusselt number is. Right. So in this way, it's very useful. All right. So let's move on. We'll move on to question number 8, which is pertaining to numerical solutions. So it is asking us to consider a second order central difference approximation to the second derivative of a function ux, where h is the grid spacing. Which of the following statements about the truncation error of this approximation is true? Is it that the truncation error is order h, order h squared, order h cubed, or order h4? Simple question. Let's take a look at the answer. It's order h squared. Of course, it's a second order thing, but how do we determine it? So let's take a look at this. So ux plus h can be expanded into a Taylor series form like this. We can say that it's equal to ux plus dou u dou x into h plus dou 2u dou x square into h square by 2 factorial plus the third derivative into h cube by 3 factorial into the fourth derivative into h power 4 by 4 factorial and so on. Similarly, u into x minus h can be expanded like this. We can say that it's ux, but minus dou u dou x into h plus dou 2u dou x square into h square by 2 factorial, then minus the third derivative into h cube by 3 factorial, again plus. So you can see all the even order terms, they will have plus, and the odd order terms, they will have a minus in front of them. So this one will be minus, but anyway, I'm writing plus here because there are many terms. So if we simply now take a sum of these two equations, what we will get is ux plus h plus ux minus h is equal to 2ux. These two terms will cancel out, and we can take a sum of these two, so it will be 2 into dou 2u dou x square into h square by 2. Then these two terms will cancel out, and here we will have 2 into the fourth order term into h power 4 by 4 factorial and so on. So now we will move this term to the left and divide everything by h square, because that's what gives us this second derivative, right? Okay, we can get it from here itself. So with a little bit of algebraic manipulation, I'll cut these 2's off, and what I need to determine is this second order derivative. So the second order derivative dou 2u dou x square can be written as ux plus h minus 2ux, because we are sending this over to the left hand side, and plus ux minus h, and we are dividing it by this h square, and we will have minus this term 2 into u the fourth derivative, and I have factorial 4 here, and h power 4 was there, but remember we are dividing by 1 h square, so an h square would be there, and higher order terms. So this is the leading order term, and if we look at that, it is order h squared. So that is why option B should be the correct answer. And that is what we truncate, hence the truncation error. Alright, so that's all for today. Thank you for sticking to the course. Let's hope to meet again next time. Thank you.